In today's video, we're going to cover the nomenclature of alkanes. Alkanes are compounds that contain only carbon and hydrogen atoms. They have the general formula CnH2n plus 2. They are completely saturated, which means they contain only single bonds. There's often more than one way to name a compound, and today we're going to talk about 3 types of nomenclature. The first type is trivial. This is often based on biological origin. Or named after a person. Or company. It gives no indication of structure. We won't really talk about trivial naming in this course. The second type is the common naming system. This is more systematic. But it has a lot of limitations on how many different compounds it can name. And we still use this system a little bit, and so we'll talk about it briefly today. But the IUPAC, or International Union of Pure and Applied Chemists, developed a systematic naming system that allows us to name all molecules and tells us a lot about the structure of the molecule as it's being named. And so we'll spend most of our time looking at that naming system. Both the common naming system and the IUPAC naming system use root words from the names of straight chain alkanes in their naming system. You can find a list of these straight chain alkanes on page 89 of your textbook, but we'll go over the first 12 of those in this video, and I'll expect you to know those. These alkanes get their names based on the number of carbons they have. So methane, or CH4, has 1 carbon in it. Ethane, or C2H6, or another way I would draw that is just a line, and remember that the ends of that line represent carbon atoms. So that's ethane, has 2 carbons. Propane has 3 carbons. Butane has 4 carbons. Pentane has 5 carbons. Hexane has 7 carbons. Heptane, 8 carbons. Nonane has 9 carbons. Decane has 10 carbons. Undecane has 11 carbons. And dodecane has 12 carbons. The table in your book has a substantially larger number of compounds in it, but I only expect you to know the first 12. Let's look at the common naming system a little bit. So butane still has 4 carbons, 1, 2, 3, 4. That is another way you might hear that is N-butane, and that just means it's the completely linear form of butane. Isobutane indicates that there's a difference in shape. And so isobutane has 4 carbons, but instead of being in a straight line, there's a carbon branching in it. Pentane has 5 carbons in a row, so that's the same thing as N-pentane. And isopentane, just like isobutane, indicates that there is a branch. There's 5 total carbons, but there's a branch there to indicate isopentane. Neopentane means there are 2 things coming off, and so neopentane looks like that, which we have already seen. Hexane, 6 carbons long. Isohexane, like isopentane, has a branch at the second carbon. Still 6 total carbons, just a branch. And neohexane has 2 branches at that carbon. Again, still 6 total carbons, just 2 branches. And so you'll notice that anything with the prefix iso has this little Y shape at the beginning or at one end of the structure. And so that indicates an iso prefix. And anything with a neo prefix has this little pitchfork shape at one end of it. And so that is going to indicate a neo prefix. In the common naming system, the number of carbons total in that structure indicates the root word that you have, which will be different in the IUPAC naming system. The IUPAC nomenclature is a systematic naming system. It can be quite complex, but it can be used to name all organic molecules. The longest continuous carbon chain is known as the parent chain, and that's where you get your root word from, and any branches are known as substituents. Let's look at the first example on your handout. Which looks like this. It's got a branch coming out there. So the longest continuous chain is going to be here. If we wanted to number those, we could start here. 1, 2, 3, 4, 5, 6, 7. And so if I look back to my notes from the previous slide, I know that 7 means heptane. Each substituent is given a number based on which carbon it's attached to, but it should be given the smallest number possible. And so I've started from the left-hand side of the page numbering here, but if I were to start from the right-hand side of the page and have 1, 2, 3, 4, 5, 6, 7. Notice that the green numbers, that methyl group or that CH3 is attached to the 3rd carbon, and so I'm going to use the green numbers as my numbering system. And it's 3, and it's 1 carbon, and so that is a methyl group. Notice that I got methyl from methane, and I dropped that ANE and added ill to get that addition. So the name of this molecule is 3-methyl-heptane. There's another molecule on that page that looks like this. Take a moment and see if you can come up with a name of that. Notice that this chain breaks or bends upwards. If I kept going straight, I would just have 6 carbons, but if I bend upwards, I have 7. And you might also notice that I ought to have started at my 7 and counted backwards to get a low number. And so this molecule has 7 carbons. It's a heptane. It's also substituted on the 3rd carbon with a methyl group. So it is also 3-methyl heptane. These molecules are the same, they're just in a different conformation. If your molecule has more than one substituent, each substituent gets its own number. We're going to use the prefixes di, tri, tetra, penta, hexa, etc. to indicate how many of those are present. And we're going to assign numbers so as to give the smallest number to the first point of difference. So in this example, I could count from the left and have 1, 2. That gives me a 2-methyl. Or I could count from the right and get 1, 2, 3 is my first substituent. And so I'm using the first point of difference. And so I'm going to continue on with the blue numbers and forget about the green numbers because 2 is lower than 3. 3, 4, 5, 6. So 6 carbons in a row means my parent chain is a hexane. On the 2nd carbon, I have a methyl group. And on the 4th carbon, I have 2 methyl groups. Each methyl group gets its own number. So I'm going to write 4, 4 right next to each other. The numbers are separated by commas, and the numbers are separated from words by a dash. So I've got 2, 4, 4 trimethyl hexane. If you have a molecule with multiple types of substituents, we're going to cite those substituents in alphabetical order, ignoring the prefixes like di, tri, and tetra. I'm again going to start by numbering my carbons. If I start from the left-hand side, I have 1, 2, 3, 4 to my first point of difference. If I start from the right-hand side, I have 1, 2, 3 as my first point of difference. And so we're going to use the right-hand side. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons is a nonane, and so I'll start with nonane. On the 3rd carbon, I have an ethyl group. On the 6th carbon, I have 2 methyl groups. Ethyl comes first alphabetically, and so I'm going to start with that one. It's on the 3rd carbon, and so I have a 3-ethyl dash 6,6 dimethyl nonane. So the name of that molecule is 3-ethyl 6,6 dimethyl nonane. This is a list of some common substituents. We've already seen methyl and ethyl. Propyl is just 3 carbons, and so we'll write 1, 2, 3, and this is where it would be connected to the parent chain. Sometimes we mix common names in IUPAC names, and we have an isopropyl substituent. Remember that isopropyl meant that there was this Y, and so that's 3 carbons, and it's connected to the parent chain through this bond here. And so this would be the parent chain right there. Butyl is 4 carbons, 1, 2, 3, 4, and then the parent chain is connected here. Isobutyl, that should say butyl, not butyl here. This should be isobutyl. um, is just like isopropyl. It's got a Y at the front and then 4 carbons, and it's connected here to the parent chain. This would be the parent carbon atom there. Sec-butyl is a little bit different. It is a 4 carbon chain, but it's connected to the second carbon to the parent chain. And so we would connect there, and this would be the carbon atom on the parent molecule. Tert-butyl is 4 carbons like that, connected to the parent chain right here. Pentyl is just 5 carbons in a row, so 1, 2, 3, 4, 5, and then it's connected to the parent chain there. This would be the carbon on the parent chain. And isopentyl, much like isobutyl, has a Y. That's 3 carbons, 4 carbons, 5 carbons, and then it's connected to the parent chain here. The ones that I really want you to remember are the N-methyls and ethyls, where they're all straight chains. And then isopropyl and tert-butyl. Those are going to be important ones for you to know. If you would like, you can pause the video here and copy down this chart. Let's look at a few practice problems. And so these are in your handout. We'll start here at the top left. And the first thing we're going to do is identify the parent chain. Remember, the parent chain can bend, and so I think that this is going to be our parent chain. That looks like the longest one. So let's go ahead and number that. 1, 2, 3, 4, 5, 6, 7, 8. If I had started at the other end, I would have gotten 1, 2, 3, 4 is my first point of difference. So I think I'm good with the place I started with. I notice I have 2 methyl groups. One is on carbon 2 and one is on carbon 5. And so I'm going to go with 2, 5 dimethyl, and 8 means octane. So that takes care of that one. In this second example, I think our straight across linear chain is probably the longest one. And it looks like my first point of difference is going to occur if I start on the left. And so I'm going to go with 1, 2, 3, 4, 5, 6, 7, 8. I've got a methyl group here and an isopropyl group here. Remember, when we're thinking about prefixes, we thinking about alphabetical order, we ignore the prefix. And so I'm going to say that P as in propyl comes after M as in methyl. And so this is going to be 2-methyl, 5 isopropyl, octane. In this last example, I think I can probably start at the left and go right all the way to number and get the right numbering system again. And so I'm going to start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've got 2 methyl groups on carbon 3 and a tert-butyl group on carbon 6. Notice that there is a little hyphen between tert and butyl. That occurs with tert and sec, but none of the others. B comes before M, and so I'm going to start with 6 tert-butyl, 3,3, remember each methyl group gets its own number. Dimethyl. And 11 carbons is undecane. So that takes care of that example. Take a stab at generating the line structure from the names in the next 3 sets on your handout, and we'll use one of those as your Plicker question at the beginning of class on Monday. Technically, using the common names as substituents is not exactly correct. And so the IUPAC naming system does have a naming system for branch substituents. If we were using the common name branch substituents, this substituent would be sec beetle. But that's not what we're going to do this time. We're going to name this using complete IUPAC naming. And so again, the first thing we're going to do is start by numbering the parent chain. I'm going to start left to right and see if that works. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I'd started the other way, I would have 1, 2, 3, 4, 5, 6. So I'm good. The other thing I need to do is to number the carbon atoms on the substituent. I'm going to pick the longest chain on the substituent and number them starting with where it's attached to the parent chain. So I'm going to start with 1, 2, 3. The substituent is always attached to the parent chain through carbon 1. And so this is a propyl, and it's got a methyl group hanging off of carbon 1. And so the way we deal with that is we use parentheses. So this is a 1-methyl propyl substituent. It's attached to carbon 5 of the parent chain, and the parent chain is a decane. So the name of that molecule is 5,1-methylpropyl decane. If we look at the next example and we start numbering our carbon atoms, I could start here 1, 2, 3, 4, 5, 6, and that would give me a 6-carbon chain. I could also start here 1, 2, 3, 4, 5, 6. That also gives me a 6-carbon chain. But the red numbers are going to give me a 6-carbon chain that do not require me to use this weird branched substituent thing because none of those substituents are branched. So if you have a way to draw the chain such that none of the substituents are branched, that's what you want to do. And so we're going to use the red numbers, and I see that I have a methyl group attached to carbon 2 and a ethyl group attached to carbon 3. E comes before M, and so this is 3-ethyl, 2-methyl hexane. In the last example, I think I'm going to have to deal with a branch substituent no matter what. And so I'm going to go with this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's a no name. I have a methyl group on carbon 2. And if we were using common substituent names, I have a tert-butyl group on carbon 5. But we are going to use the IUPAC naming system. And so I'm going to number the longest chain on my substituent, which is just 1, 2. Ethyl group with 2 methyls attached at carbon 1. E comes before M, and so I'm going to start with this branched ethyl group substituent. And that's attached at carbon 5. So I'm going to start with 5, parentheses, 1,1, dimethyl ethyl. 2-methyl. This was 9 carbons, nonane. The last thing I want to talk about is nomenclature of cycloalkanes. And in this, you're first going to have to determine if the cycle is a substituent or the parent chain. And so I am going to start by counting the number of carbons in my cycle. There's 1, 2, 3, 4, 5, 6 carbons in my cycle. There's only 1, 2, 3 carbons in the straight chain. And so my cycle is going to be the parent chain. If there's only one substituent, I don't need any numbers. And so I've got 1, 2, 3. That's a propyl group. This is propyl, cyclohexane. I added the cyclo in front of hexane to indicate that it was circular. In my next example, I can see that there are only 3 carbons in the circle, and there are many more in the parent chain. And so I'm going to assume that that cyclopropyl group is a substituent, and I'm going to number my parent chain 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a nonane. So that is 2 cyclopropyl nonane. The last example we have is way more complicated than the first 2 cyclo things that we looked at. So let's get started. There are 5, 1, 2, 3, 4, 5 carbons in my cycle. The largest substituent I have is 1, 2, 3, 4, and so my cycle is going to be the parent molecule. I have multiple substituents, so I'm going to need to number. I'm going to start numbering, and this time we want to minimize the total numbers of carbons. And so I'm going to start with 1 where I have 2 substituents. And so that's going to keep my 1,1-dimethyl real small. I'm going to go counterclockwise or to the left because my next substituent is on 2, 3, 4, and 5. If I had gone clockwise, I would have 2, 3, 4, 5. I would have substituents on 5, and this way I have a substituent on 4 as my highest number. On carbon 1, I have 2 methyl groups. On carbon 4, I have an ethyl group. On carbon 5, I have a branch substituent. I'm going to number my carbons. 1, 2, 3. That's a propyl group with a methyl coming off of it. So to go in order, we have to start with ethyl. And so this is 2 ethyl, 1,1 dimethyl, M comes before P, 2, and I've got to have parentheses. There's a methyl on carbon 1 of my substituent, so 1-methyl propyl. Cyclopentane. So that name is 2-ethyl, 1,1-dimethyl, 2, 1-methylpropyl cyclohexane. That's a mouthful, but that is the name of that molecule using IUPAC nomenclature. I think that'll wrap up the video for today. We will pick back up in class on Monday.